All right. Bismillahirrahmanirrahim. Assalamualaikum. Good afternoon, everyone.
Salam. Good afternoon, Doctor.
Okay. Again, I'm not so sure how clear is it. The sound of my background because there's a construction going on at the moment. But please, if it gets too loud that you cannot hear my voice, please let me know. Yeah. Okay. Um. All right. So okay, let me start the recording first. Second. All right. Okay. As you all know, we have started doing our lab viva this week. So I believe that you have received my announcement in the Telegram, saying that even though that you are working on the solution separately, so meaning that you divide your work among the members, please make sure that before you go for your for the Viva session, um, 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 have your members to present what they have found and what they have prepared for the lab. Okay, because supposedly the question should be asked randomly on any members. So it is expected that all the members must know, not know lah, but somehow able to answer all the question despite whether or not they are preparing for that question. Okay, is that all right? Class.
Okay. Okay.
Okay. All
Okay,
right.
Doctor.
All right. So that is about the lab viva. And then I just wanted to, like make a quick survey in regards to alternative assessment. Okay, so for the alternative assessment, I'm not sure how other courses that you're taking right now is planning to do the alternative assessment. So initially we plan it to be within the 14 weeks of class of our class. So I'm not so sure whether you prefer it to be before week 14 or if you want to do it after week 14 in this case. Can I have a quick, reply from you within 1 minute?
After week 14.
100% after.
100% after. Okay, can you just or maybe I create a poll later, or maybe I don't know how to create a poll in the Telegram. Did anybody know? Let me try and see if I can create a poll right now in the Telegram. What's my Telegram? Okay. So like the access. No, I'm not. Okay. Oh yeah, I can create a poll. Okay. So I will create a poll. Alternative assessment. Before, let me just like quick one. Before or after week 14. Option before, after. Okay. Okay, so I've sent a poll in the Telegram. So please give your feedback. Okay. So before, after we can save time taken in the poll just to make it after. And just make it after. Okay. Based on the poll, The question will be given, of course, before week 14, so that at least we will have time to prepare if, to have to see the question. But then the submission, meaning the submission, whether you want it to be submitted before week 14 or after week 14. So before week 14, meaning it's not like by week 14 you have to submit. Maybe we'll do it earlier, like maybe week 12 submission or week 11 submission or something like that. Okay, so please give your feedback in the poll. All right. Okay, so that is the two things I wanted to say before we start our class for today. So I believe that since I have nobody like nobody like actually came forward if they have any problem regarding last week. So I assume that everyone is okay, which is good. So so I'll see you during Viva. All right. So today we're going to be looking at another topic, which is the divide and conquer algorithm. To be honest with you, it is not actually like new. I think we have looked at I think one or two divide and conquer algorithm in the previous lecture, but it's just that today we're going to be specifically looking at the divide and conquer algorithm. Okay, several divide and conquer algorithm, and we will see the characteristic of a divide and conquer algorithm. Okay, so today, as I mentioned, it will be divide and conquer, and we will be looking at merge sort. So as I mentioned, we have somehow see a little bit, look into merge sort a little bit, and we're going to be looking at quick sort, and then heap and heap sort. For the binary search, I think we also have looked into this one in not look lah, but somehow we discussed about this a little bit in our tutorial, if I'm not mistaken, about the binary search. Okay, so these are some example of a divide and conquer algorithm that we're going to be looking at today. All right. So first of all, when we talk about algorithm design and paradigm, we are actually talking about the high level, what are the high level approach that we can take in order to solve a certain class of a problem. Okay, so some of the common ones that you can find are the divide and conquer, the dynamic programming, and the greedy algorithm. So these are the three classification of algorithm that or an approach of an algorithm that you can use in order to solve a certain class of a problem. Okay, and then there's also brute force backtracking. Okay, so we don't really brute force. Sometimes we're going to be brute force can also be. I think we will look into a little bit about brute force in greedy algorithm. Backtracking, I don't remember, but I know we will be looking at one example of backtracking in one of these approach. Okay, so but the main ones that we're going to be looking at in this course would be the divide and conquer, dynamic programming, and the greedy algorithm. Okay, so for the divide and conquer, as you can see here, it is actually an approach where you recursively break down your problem into two or more sub-problem of the same type. Okay, and then there will be no overlapping of the sub-problem. Okay, so I believe I also mentioned about, when you talk about the divide and conquer, you have, I think when we talk about recursive function, okay, on how you have a big problem and you try to break it down into smaller problem. Okay, sub problem 1, sub problem 2, sub problem 3 of the same sub problem of the same type, and then you merge it back. Okay, so that is the concept of a divide and conquer algorithm. So later on you're going to see in dynamic programming, it is breaking down a problem into a simple problem as well. It's just that the only difference is that in the dynamic programming, we have to make sure that our sub problem overlaps. Okay, so we're going to be looking at dynamic programming later. as well as the greedy algorithm, which is we try to make a decision locally, okay, meaning locally optimal decision at this stage. So for today, we're going to be looking at the divide and conquer. All right. So for the divide and conquer, the concept is pretty simple. Okay, we have the divide step, the dividing stage. Okay, where you divide the problem into sub problem. And then the second step is you conquer the sub-problem by solving them recursively. And then the final step is we combine the sub-problem solutions. Okay, so basically these are the three major steps of a divide and conquer algorithm. So later on, you're going to be able to see that each of the algorithm that we're going to be looking at today will have these three steps. Okay, either the dividing steps, the dividing stage, and then the conquering stage, and then afterwards the combining stage. Some of the algorithm, maybe you will see that the combining it's pretty trivial, or the during the divide is trivial, but whatever it is, for a divide and conquer paradigm algorithm, divide and conquer algorithm, normally will have these three distinct stages. Okay, so let's look at the divide and conquer algorithm, the first one, which is the merge sort. Okay, so for the merge sort, uh, uh, specific, of course, it will have the three stages. Okay, but for the first step, which is the divide, it is pretty trivial. It's just that you have an array and then you will divide it into two. Okay, and then for the second stage, for the second step, which is the conquer, is where you will recursively sort between the two subarray. After you have broken down the array into two, okay, recursively break down the array into two, and then you will recursively sort those subarrays. And then after that, you're going to do the merging. Okay, so the merging will be in linear time. All right. So let's look at the merge sort algorithm here. Okay, so for the merge sort algorithm, okay, so as I mentioned, as you see just now, the step for merge sort, the dividing part is pretty trivial. The reason why, if you see here in the pseudocode, okay, for the merge sort, you check whether you still have you have some elements. So the P is the first element and R is the last element. So if you have P is lesser than R, meaning that you still able to break the array into two. Okay, so the dividing is at this line. Okay, whereby you just take the size of the array. Okay, and divide it by two. Okay, floor divided by two, and then after that you just keep calling the merge sort, and you send in the P and Q, and the other one, and then you call it another merge sort, whereby you call A, Q plus 1 and R. So what does it mean is that if, like, let's say you have this array, right, of P and R, right, and then you find Q, so you find the middle part, which is Q, and then you call a merge sort on this array, we call it array A, and we call another merge sort of array B. Okay, so you send in these two, and you keep dividing it into two. So this one, you find another, this one will be PR, and then you have Q, and then you will have maybe A2, B2. Okay, and you keep calling the merge sort. Okay, and then once you get into the part whereby you have two distinct elements, and you will merge it back. All right, so basically that is what a merge sort do. So you will keep dividing, and then after that, the second step would be to merge back the subarrays. Okay, so the merge function would be defined here. Okay, whereby you will recursively try to compare and merge it back the subarray. All right. So let's try to look at how the merge operation occur. All right. So like let's say we have this array. So we have this array. So let's say we have this array and we have broken it down to these two subarray, okay, left and right. So how do we merge it back? Is that first we look at the left and right, okay, and we compare which one is the smaller and which one is the bigger element. So we have a pointer I and j here, and we compare. So if we which one is smaller? So since this one j is smaller, we will put one inside here, and we do another comparison. We move our j, and then we compare again. So if we see which one is smaller, so in this case, both of them are 2, right? So we're going to put these 2 here, okay? And we're going to move our I here and our j. We will do the same thing. We're going to compare it again, okay? We're going to compare I and j. And this time j is smaller. So j, now the 2 would be up. We will merge 2 up. So this one is fine. And we're going to move our j and I. We're going to compare again. Okay, so basically that is how we merge it back. So as you can see, the merging is linear, meaning in a sense, all we have to do is that we just have to traverse through the element and compare it, and whichever that is smaller or the bigger, it depends on the how you want to sort your array. You will just merge it back up. Okay, so basically that is how you do the merge sort operation. So in the end, you will get the sorted array. Okay, so in the end, after you do it until the array the subarray finishes, you will get the sorted array. Okay, so up until now, is there any question that you don't understand, class, in regards to the merge sort?
Sekejap.
You want?
Doctor,
Yes.
based on this diagram, so it just splits to half and then it sorts, and then if it's not, or if it's not in the correct order, it splits again to half and then it sorts again like that, or how?
No, it will break until you will only have 2 elements in the end. So basically, if like let's say I have, okay, so let's try and do this from the beginning, because this one is already skipped. It's like you already merge it back until the last stage where it merged back to the whole array. Okay, so like let's say for example, I add 1 here. Oh, where is it? So let me try to add page after. So, all right. So let's say, so what is the array here? Maybe let me try to like, oh no. Why is it copying just my highlighting? Sorry. Copy, and then, okay, so let's try and do this one. So imagine that this, because if you notice this one, the array is already somewhere in the middle, right? But let's try to imagine that we have this array, okay? And we want to do merge sort on this array. So what we're going to do is that we're going to divide this into 2 subarray, which is we're going to have 2, 4, 5, 7 here, and 1, 2, 3, 6 over here. So this will be the 2 subarray that you will be dividing. Okay. Please bear in mind this is going to be a different question, because just now that one it will be the last step before it actually merge the whole thing. So I'm just going to use this example to show how it happened. Okay. So then we have these 2 subarray. we are going to break this down into two more. Okay, so we have 2 and 4, and we have, sorry, we have 5 and 7, and we have 1 and 2, and we have 3 and 6, and then finally we have 2, 4, 5, 7, 1, 2, 3, 6. Okay. And now this one we are going to merge it back. Okay, we're going to merge these two. So basically, in order for us to merge these two, 4. So we compare 2 and 4, we're going to get 2 and 4. We compare 5 and 7, we're going to get 5 and 7. We compare 1 and 2, we're going to get 1 and 2. Okay, so we compare 2, 4, we're going to get this. We compare 5, 7, we're going to get this. We compare 1 and 2, we're going to get this. We compare 3 and 6, we're going to get this. Okay, and then this one, this level is done. We're going to merge, now we're going to merge this level. Okay, and then we're going to merge 2 with 5. Okay, so we have 2, we put in 2, and then we move our, this one is I, right? So we move our I, now we compare 4 and 5, we're going to put 4, and then we compare 5 and 7, we're going to get this array. Okay, and then same goes for this one, we're going to compare I and J. So 1 is here, so we're going to put 1 here, and then 3 with 2, and then we found 2 is smaller, we're going to put 2 here, and then 3 and 6. So we get this array. Okay, so this is the one yang we do here. We got 2, 4, 5, 7, right? 2, 4, 5, 7, 1, 3, 1, 2, 3, 6. This is where you're gonna do the IJ just now. Okay, so before you actually get into this step, you already break the array down until this level. Is that all right? Who was asking the question? Yeah. So that is how you do the merge sort. Okay. So just now what we did was here at this level. Okay, we already get back to that one final level before it merge back into the array. Okay, so that is the merge sort operation. Okay, so as you can see here, this is how we do it. So we break it down until the last level, and then we merge it back. All right, so this is the merge sort operation. All right, so do you remember how do we write our running time complexity for recursive function? Anybody wants to try to write what is the running time complexity for merge sort? Do look at the slide. The next slide there's an answer, but if you want, anybody wants to try and write the running time what is that word? Running time complexity, the relation equation for merge sort. Anybody wants to try it? As you can see, the problem is being divided into two. So how would you write the recursive equation? And anybody wants to try it? So we know that the running time complexity is where we will break our problem into two, t of size what? We are breaking this one down of size. We have n, and how do we break it down? The recursive breaking down class?
Half, so divide by 2.
N over 2, yep, plus how we merge it back would be order of
The level, wait.
Yeah, each level
levels.
we will merge it back with according to the number of element, right? So therefore, the merge sort, the recursive relation will be will look like this. So based on master theorem, what is the running time complexity for merge sort? Master theorem? It will be class. Or normally, if we imagine the recursion tree, what is the running time complexity for this kind of it will be n log n, right? So the running time complexity will be order of n log n, right? Okay. So basically, like we discussed, so the sub problem is two. Okay, so we have two sub problem that we divide into two. The array we divide into two, and then order of n of work of the dividing and the combining back of the solution. Okay. All right. So what is the classification of merge sort? Remember the 4 or 5 classification that we have that we learned in regards to the sorting algorithm. Can someone give me like an example of 1 or 2 classification that we can uh, class the merge sort into? Is this in place, class? Is this in place, sorting algorithm? It's not in place, right? What else? Is this a stable? It's stable. Okay, what else? Can you say about the classification of merge sort? Adaptive?
No, not
Not really
adaptive.
adaptive, right? It's not adaptive. Anything else? Anything else? Adaptive, and we have online or offline. It is an offline algorithm. Okay. All right. So think as well about whether the condition of the input will affect the running time complexity of a merge sort. So I leave that to you to think about that. Okay. So that would be the merge sort. All right. Okay. So the next divide and conquer algorithm that we're going to be looking at is the quicksort algorithm. Okay, so the different of on so as I mentioned, I think I mentioned this before. I kind of like this quicksort because the properties are quite nice. Okay, but when you do the analysis, it looks like uh it will run at least the average case. It will still have the average case running time complexity uh, uh, in most of the cases. Okay, because even though that you're already moving towards the worst possible cases, the quick sort will still somehow runs in the average case, just like merge sort, which is n log n. Okay, so we're going to be looking at the analysis later. But first, let's look at some introduction about quicksort. Okay, so it is proposed by I always cannot pronounce his name. Hoare in 1962. Okay, so uh, unlike merge sort, this quick sort will be sorting in place. So all of you, the sorting will occur within the same array. Okay, and they are very practical. Normally, for quicksort, the performance is good. Okay, especially if you are able to tune it, it can really be very good. A very good sorting algorithm that you can use for sorting. All right. So for quicksort, okay. So again, it is a divide and conquer algorithm. Therefore, it will have the three stages, which is the dividing stage. So for unlike merge sort, the dividing part is very trivial. All you have to do is just break it into half. Okay, but for quick sort, it has this mechanism called the partition. Okay, where you do the partitioning into the two subarray around this what we call a pivot element. Okay, a pivot element, and whereby in the after the end of your division, okay, where after you finish divide the subarray, you will have uh, elements in the lower subarray before the pivot value x will be lesser, okay, and the elements in the upper subarray will be more than the value of x, okay. And then after that, how you do this is you recursively doing the sorting of the two subarrays, and then when you combine it is trivial. Okay, the reason why is that because after each of the step where you have found the location of x, the pivot value, okay, in the subarray that you have sorted, the element is already in its correct position. Okay, so therefore that is why the combined step is very trivial, because after each of these step, after each of the recursive calls, okay, your pivot value will be at its correct position in the array, okay, the sorted array. So therefore that is why they call the combination the combined stage is very trivial. Okay, so the key here is that we're going to be using a linear time partitioning subroutine. Okay, so again, later on we're going to see that how we're going to do this. Okay, linear time partitioning subroutine. Okay, so here is the algorithm for quicksort. But before that, I did remember that someone mentioned that you have looked into quick sort in data structure. Is that true, class?
Yes, doctor.
So data structure you implement the quick sort, is it, class? What did you look
Yes,
at?
we did learn about quicksort and also merge sort.
Oh, you learn about merge sort and quick sort as well.
Yeah.
Okay, all right. Okay, so it will be much easier for you to sort of like understand this quick sort as well as the partition. Okay, so because I this is actually the first time that somebody told me that they have looked into quick sort in the data structure. I don't know whether they just add it, or is it that they have teach this before, but my student never mentioned it to me. Okay, all right. Okay, so as I mentioned just now, for quicksort algorithm, the dividing is the most important part, which is where you do the partition. Okay, so if you look here in the quicksort, the first thing that you have to do is you are going to do the partition. Once you have done the partition, you're going to call the quicksort of that partition again and again until you finish doing the sorting, okay, in each of the sub array. All right, so let's look at how you do the partition. Okay, so as you all aware, especially if you have looked into this during your data structure, so you may find different implementation of the quicksort, okay, in terms of where do you get, or where do you put the pivot element and so on and so forth. All right, so in this case, if you look at this algorithm, we choose the pivot element as the last element in the array. Okay, so if like let's say this is your input array, so the x would be the last element inside the array. So this would be the pivot value. Okay. So all right. So with that clear, so let's try to do a partition for this array. Okay. So let's say for example we have this input array. Okay, and then we are going to partition this into two sub-array. Okay, so maybe let's try and do this together. Okay, I'm trying to find better not. Okay, page after. All right. Okay, so let's say we have this. What is this? So let's say I copy this. All right. Okay, so let's try to do this. Why I cannot make it bigger? Okay, all right. Is that big enough? Okay. So let's try and partition this array. Okay, so we have our I, we have our, this is our P. P would be the first element, R would be the last element, and our pivot is actually the last, our pivot value is the last element in the array, which is 4. Okay, and we have pointer I and pointer J to do the uh, um, the traversing. Okay, so how we're going to do this is that um, can you give me like 1 minute? I'm so sorry. Let me try because I have something. Is it okay? Can you give me 1 minute? I'm so sorry.
Okay.
Yeah.
Okay.
Okay, doctor. All right. All right. Sorry for that. Okay. So where were we? Okay. So we're trying to do partition onto this array, right? Okay. So we have pointer I and pointer J. So basically, what we're trying to do is that basically we have four generic steps. Okay. To do. Okay. So first one is we are going to compare. We are going to compare A, J with our X, okay, which is the pivot value. And then the second one is that we're going to check, okay. So if our A of J is lesser or equals to X, okay, we are going to do this. We're going to do I plus plus, and then we're going to swap A of I with A of J. Okay, this only occurs if this is correct, and then after that we're going to move our J, and once we reach the end, we are going to swap. We're going to swap our X with A I plus 1. Okay, so basically these are the steps that we're going to do if you want to do the quick sort. All right, so okay, so let's try and do this quickly. So we have our I and our J and our X. Okay, so now we're going to do this. All right, so first we are going to compare AJ with X. So we're going to compare 2 with 4. All right, so if AJ is less than X, is AJ less than X? It's correct, right? It's true, right? So therefore, we are going to move our I. So our I is going to be here. And then after that, we're going to swap AI with AJ. So our AI is 2. Our AJ is also 2. Therefore, there's no swapping. So 2 would still be there. Okay. And then we're going to move our J. So now our J is here, our I is here, and our X is still there. And we haven't reached the end. We're going to continue doing that again. Now we're going to we're going to compare, we are going to compare 8 with 4. So is it that AJ is less than X? It is no, right? So therefore, we are not going to increment I or swap AI with AJ. We are just going to move our J. Okay, so we're just going to move our J. All right, we'll do the same thing again. We compare 7 with 4. It's not smaller than X, so therefore we are not going to do the I plus plus. So we're just going to move our J to the next one. Now we compare 1 with 4. So this time AJ is smaller than X. We are going to increase I. We're going to increase I plus 1. Okay, and then we're going to swap AI with AJ. Okay, so our AI is 8. So now AI and AJ, so this will become 1. This will become 8. Okay, and then J plus plus. We still haven't reached the end, so therefore we're going to do the same thing again. All right, compare 3 and 4. It is smaller, so we're going to increase I. We're going to increase I. And then we're going to swap AI and AJ. So now this one becomes 3. This one becomes 7. Are you following so far? And we are going to increase J. So now J is here. Okay, still haven't reached the end. We're going to do the comparison again. So 5 with 4, AJ is bigger. So we are just going to move the J. J is here. We're going to compare 6 and 4. Still, 6 is bigger than X, so we just increase our J. And finally, J reach the end, right? So once J reach the end, what we're going to do? We're going to swap X with our A, I plus 1. So I plus 1 is this, right? So now we're going to swap 4 with 8. So now this one is actually 4. This one is 8. Okay? And then you finish doing your partition. So now what happens here, you can see that whatever element inside this subarray is smaller than 4, and whichever that is on the upper side of this subarray would be bigger than 4. Did you notice? Okay. So basically, you have done the first partition. And what you're going to do is that you're going to do the same thing again for this, for the subarray that is in blue. And you're going to do partition again for the subarray in orange. This 4 is already in the correct position. So every time you do this, whenever you have the partition and you keep doing this, in the end, you will get the pivot element in the correct position. So that is why after you finish doing the partition, recursively doing the partition and sorting the subarray, all of the pivot element will be in the correct position, and that's why the combined phase, the combined stage of the quicksort is trivial. Okay. So is that all right, class?
Doctor, since now the last element in the array is the biggest number, and the rest of 3 of the elements is not sorted. So how since like once we go through everything, it still won't be sorted. So how do we? So it's like our pivot then move one step inwards.
No, we are not going to consider the pivot anymore. So now so the next one, our P and R would be here. Our P is here, our R is here, and this is our Q plus 1. So this one, according to the the pseudocode. Okay, so A and P. This is PQ minus 1. This is now the next call would be P. This is Q minus 1. Remember, this is Q just now. Q minus 1. And then this is Q plus 1 to R. So we are not going to consider this anymore. The next one, the pivot value, if we look at the pseudocode, it will consider the last element in the array, right? Which is 3. Then in the next partition, the 3 will be in the correct position. In the next partition for this subarray, the 8 is going to be in the right position. And then you're going to get another subarray again after the partition. And you're going to do the same thing again. So basically, after end of all those recursive calls to do the partition, all the pivot value will be in the correct position. Is that all right?
Okay.
You try and continue doing this again for until it finishes, until all the elements is in the correct position. Okay.
Oh, so that means now the unsorted part is the one we look at. The ones on the inside we ignore completely.
This is not sorted. This one is not sorted. It is just that this one is, all the element will be smaller than this element. All this element will be bigger than this element. It's just that, but it's not sorted.
Okay.
So in a sense, you're going to do the same step again, all this step again for this subarray, and the same thing for this subarray. And you keep doing this until all the elements are in the correct position. So basically, once you complete until the last step, you should get the sorted array. Try and do this. Try to continue doing this, following the step for this one as well. So you will keep having partition, dividing it into two subarray until you finish all of the elements. Okay. Any question, class, about the quicksort?
Doctor.
Yeah.
So after this, for the blue part, the X will be 3, right?
Yeah. For this subarray.
Yes.
For this subarray, the X would be this. For this subarray, the X would be this one, according to the pseudocode.
Right. Understood.
And then the next one, you will also have another two subarrays, same thing. So you keep doing the recursive call until you finish all the elements. Okay. All right. So that is for the quicksort. All right. So how do you think the running time complexity of this quicksort is going to be? Can you actually write the recursion relation for quicksort, class? Do you think you can write the the relation for quicksort? Is it something like merge sort? Merge sort is pretty easy. You definitely will divide it by 2. For quicksort, how do you write the recursion relation for quicksort? Any ideas? No. Okay. So if we look here, yeah, it is not exactly divided by half. Ideally, we would want it to happen, but somehow, if you look at what we did just now, it's, we cannot determine for sure that we're going to be able to have the partition and the pivot value to be right smack in the middle of the array, right? But okay, but in order for us to do the analysis of the running time complexity for this particular quicksort, okay, so we have to assume that all of our element is distinct, so there are no repeated elements. The original algorithm for quicksort actually supports the duplicated elements, but the way they do the pointer is a little bit different. Okay, the way they traverse the array is a little bit complicated. Concept is still the same. It's just that the way they traverse the array is a little bit different. So the one that we have here, that we see at the moment, is a little bit simpler, that we can see with that for us to understand the concept of the quicksort. Okay, but for now, for this particular algorithm, we assume that all of our input elements are distinct, and then we can say that the in each of the partition, we can have one side to be some numbers of subarray, okay, some number of elements inside the subarray, plus with some numbers of elements in another subarray. Okay, so there's a combination. It's either k, t, n minus k minus 1. Okay, so there's a combination whether if, like, let's say we have 8 elements, so maybe the subarray we're going to get 6 to 2, 4 to 4. Okay, so the combination would be vary. So that's why we put it as such. And then we have the order of n, whereby, like to do the sorting, or the how do you call that, the traversal and the swapping. Okay, that will be order of n. So basically, we can say that the recursive relation equation for quicksort can be written as Tn, whereby the Tk plus Tn k T minus n, n minus k minus 1 plus order of n. Okay, because the running time complexity will depend on how your partition works. Okay, how do you actually do the partition? What kind of partition that you're gonna get? Okay. All right. Yeah. So when will we gonna get worst case behavior in quicksort? Class? Any ideas?
When it's the exact reverse of the order we want it to be. Like, say if you want to be ascending order,
Uh-huh.
like if you want to be ascending order, but the current order right now is descending. So since the smallest number will always be at the one end, so all numbers will like gather at one spot, and so we need to consistently push things around. Yeah.
So in a sense, this just like you doing insertion sort, right? So so in a sense, it doesn't really matter whether it is descending or increasing order. It's just that if you have somehow a sorted list, then you're gonna get the worst case running time behavior in quicksort. So what is the worst case running time behavior in that case if we have that issue? Plus? Here? we're gonna get order of n squared, right? Something like a normal sorting order. Okay, whereby if like let's say we have a sorted or reverse sorted input, and every time the element that we get is that after each of the partition, you will have no subarray on the upper or the lower side, and the rest of the subarray, the element in the one side of the subarray. Okay, if you have the input sorted or the reverse sorted input. Okay, whereby you need to partition around the min and the max element all the time. Okay. And as I mentioned, one side of the partition will have no subarray. So basically, the next one you're gonna get. So basically, this you're gonna get something like this. You're gonna sort this one again, and you're gonna get the pivot, the X here, right? So this is where you're gonna get the worst case running time for quick sort. Okay, so if we try to use the back substitution method, so we're gonna get something like the arithmetic series, and we're gonna get order of n squared, the worst case running time complexity for quick sort. All right. Excuse me. Okay. So if we try to draw the tree, we're probably going to get something like this. Okay, whereby the branch will be like on one side. So therefore, like we can basically try to guess what is the running time complexity for that one. And then the reason for this is that later on we're going to see. Okay, so if it is the case whereby we do not have any subarray, okay, on one side and the rest of element on one side, okay, so this will result in the order of n squared, which is the worst case running time complexity for quick sort. Later on, we're going to see that, let's say if we can, the average case, how far can the average case condition be for the quick sort to not reach the worst case running time, which is order of n squared. Okay, so let's bear in mind this is the worst case tree for quick sort look like. All right. So the reason why I said that this quick sort is very interesting is that when we try to analyze the best case and the average case, it gives us a very nice property. Okay, so of course, if you remember when we start our course, I think I did mention this in our topic one, whereby we were talking about best case, and we don't normally look at best case because they are trivial, and it rarely happen, or maybe it doesn't happen. Okay, the best case analysis, but for this case we are just going to do it for intuition. Okay, we try to understand the characteristic or the properties of the quick sort. Okay, for the best case analysis of quick sort, as you can see, like as you mentioned, because I think one of your friends already mentioned here in the chat, whereby for quick sort, the division of partition doesn't necessarily occur in the middle. Okay, but then ideally, for the best case, if let's say quick sort can, when the partition, you can actually have the partition right smack in the middle, the running time complexity or the recursion relation may look something like merge sort. So you can say that it is 2n over 2, and then order of n of those swapping and comparison. Okay, and therefore the running time complexity that we can say, the best case is order of n log n, okay, which is the same as merge sort. Okay, so, and we know that for the worst case, it happens when there's only one side subarray. Okay, one side there's no only one side of the subarray is being generated during partition. So you know that that is the worst case. Okay, so it's either in the middle, or and then the worst case the other end is no, and all the rest of the array element in one side. So let's see if, like, let's say we have a condition where, let's say for example, we have 10 element, okay, and then the split is at least always 110 to 910. Okay, so meaning that whatever it is, the split will somehow have one element on one side. Okay, so no matter what, you after you split, you will still have one element, uh and then you will have one element, and so on and so forth. So this is what it means. So what happened? Are we still going to, what is the running time complexity for that? And we know that if there is no, we are going to achieve the order of n squared. But what if we always can make sure that at least we can get at least one element in one of the subarray? Okay, so let's try and analyze that one. Okay, so are we actually going to reach order of n squared? Okay, so let's look at this recursion tree. Okay, remember about your recursion tree? So if we try to, yes, don't forget the attendance. Okay, so if let's say we try to draw the recursion tree. Okay, so we have the Cn and we're going to divide it into 2, and we get on this side is 1/10, 9/10, and we keep dividing it. We get 1/100, 9/100, 9/100, 81/100, and so on and so forth. And we know that since the tree is not going to be balanced, so we know this side is going to be shorter, this side is going to be longer, right? And we know, like, basically the height of this tree, we know that normally our height would be log n base 10, and on this side we're going to get log 10 base. So the height on this tree would be log n base 10, and on this side is log n base 10/9. Okay, so if you see here, if we try to calculate the running time complexity, we are still going to get n times log n 10/9, right? Which is equals to n log n. And therefore, we're still going to get a good running time complexity, because the running time complexity will still be within the range of n log n. Okay, so do you see how far that this quicksort allowed you to stretch the condition of the partition? So even though you get only one element on one side, each time you do the partition, you will still be able to get the n log n running time complexity. Okay, so that is the nice thing about quicksort. All right, so meaning, in a sense, the condition of the how do you call that, the array is stretched quite far. Okay, and it will still be running in n log n. And again, if, like, let's say you get the case where you get a good partition and a not good partition, meaning, in a sense, some partition you will get at least one element, and some of the partition you will not get. You will get that one side and only one side of the partition, only one side of the element. Meaning, no, all the element is being divided, partitioned into one side. Okay, so basically, so in a sense, if we have that situation as well, we're still going to get n log n. How? So let's try to do a back substitution. Okay, so let's say we have, let's say for example, for a good partition, we probably can say that we get 2 of not good partition over 2 over n, and we can say that for a not good partition, whereby we say that this is n minus 1 plus n squared, order of n, okay? And then we try to do the back substitution. We put in the n of n here inside the first equation. This is the first equation, this is the second equation. So if we try to solve this, finally we're gonna get n log n. So therefore, whatever it is, even though that you're not gonna get good partition all the time, meaning at least one to the rest element of division of the subarray, you will still get the n log n running time complexity for quicksort. Okay, so that is why I said that quicksort, the running time complexity is very good. The properties of quicksort allows it to be good in most condition. Okay, so yeah, let's. Do you want to take a break for a while, like a few minutes, 3 minutes, 5 minutes? Is that right?
Yes, Doctor.
Okay, all right. So let's take a break for like 5 minutes. Okay.
Okay.
Okay, so far, do you have any question in regards to, sorry? All right, so any question do you have in regards to, why is my, sorry. All right. I don't know why the what in the on my iPad the speaker was switched on. Okay. All right. So do you have any question so far in regards to the quick sort class?
Uh, can you do a quick explanation again on the solving part of this?
The solving part.
Yeah, this one. The if one part good, the next part bad. Just a quick explanation, quick recap again.
Okay, so for the intuition in this, because I just want to show you, okay, we know that for a quick sort to have at least to still have the n log n running time complexity, you need to have at least one element in one side and the rest of the element on the other side. So at least if you have the partition and the two element and both side got some elements, okay, in that case we still should be able to get that n log n running time complexity. Okay, but what if it in some of the recursive call you might get unlucky, you might not get the at least one, maybe you will get only one side subarray, okay, all the elements into one side of the partition, okay. Will that still be, like the running time complexity will still be within the n log n? Okay, so that is what I'm trying to do here, whereby I try to define an equation for a good partition, whereby we would have some, at least some partition, okay, maybe not n over 2 all the time, but some n over 2 and some not good partition, okay, in the quick sort. And we define the not good partition as some n minus 1 uh, plus n, okay. And then we solve it just like a normal using a normal back substitution, where I put in this equation into this, okay, and I get this, and basically I solve it like using back substitution. So 2g n over 2, okay, you just put everything in the first equation. So in a sense what happened here is 2 into equation 1, and then in the end, after you solve it, you will still get the n log n. So here I'm just trying to show you the property of quicksort, whereby if let's say you still have the unlucky partition where you have only one side of the subarray, sometimes you will still get the runtime complexity within the n log n running time complexity. Is that all right? Yeah.
Yes. Yeah.
Okay. All right. So, okay. So the question here, how can we make sure that we always have a good partition, at least? Do you have any idea? So if like, let's say, so, like how do we like try to avoid the worst case, which is the sorted array? How would you think, how do you think, how do you think that we can try to avoid the worst case? Class, any ideas? Since we know that is the only thing that will get us into the worst case. Class? Any ideas? No idea. How about the rest? We know that how do we get the worst case situation again? Try to remember. How would we get to that worst case? Class? I still have the class with me? I know it's almost
Yes, yes.
4. Yeah, it's not almost 4, it's already 4, almost 5. Choose the appropriate pivot, right? Okay, so just now we know that our pivot value is that in order for us to get the worst case, if like let's say the pivot value is always either the maximum or the minimum in the array, right? So how do we actually choose the appropriate pivot? Any idea?
Find the maximum value in the element, divide it by half, and then choose an element that has this closest number to it.
One of the way pick the middle one, choose randomly. Okay, so choose the appropriate pivot. Just now your friend said we do some calculation and find the middle one. That one I'm not quite sure what they mean by nearest to it, because we unless we know how is the distribution of our input array, maybe we can do that. But if we don't know what is the distribution, or maybe the distribution, like it's not what, so perhaps I'm not sure how we can do that. But it is pick the middle one. How do you actually pick the middle one? So in a sense we have to add another more function to find the middle one, right? Choose the middle index in the array. Yes, one of the way we can always choose the middle index in the array. That is one of the way. And then yes, another way to ensure is that we choose the pivot randomly, right? We can randomly choose which element as the pivot. Okay, so there are many ways on how we can make sure this, and one of the way is that most of the time we can just use uh, uh, random. Okay, even the middle you still have pattern. So what if the way that the array is being the input array is being the condition of the input array will have some kind of pattern whereby the middle index will be the maximum. I don't know, it could be like that as well. So if we choose randomly, then perhaps the only thing that can get you the worst case is your random number generator. Unless you're very unlucky and your random number generator always generate the maximum or the minimum number element of the array. Okay, so basically if we use random element, we can say that running time is independent of the input order all the time. Okay, so therefore we can assure that at least we're going to get the lucky unlucky partition. All right, no assumption to be made about the input distribution. So as I mentioned, if we try to choose the middle index or so on and so forth, or maybe the distribution, let's say you say, like try to find the middle value and so on and so forth, so we do not have to care about what is the input distribution. We are not going to have any specific input that can get our worst case. And then the only thing that will be affecting our worst case is the random number generator, which is normally it is very, like unless you're very, very unlucky to actually generate number that will give you the maximum or the minimum number in the array. Okay, again, I want you to think about the classification of quicksort. So maybe I need to like rush this through, so you can try to think this outside of our lecture. All right, so let's look at another algorithm. called the heap sort. Okay, so the nearest running time complexity that is quite fast, that is comparable to the quick sort, is the heap sort. Okay, even though like you will find somebody said that heap sort are better, or maybe quick sort are better, but basically heap sort are the nearest comparable algorithm to quick sort. Okay, so that's why we're going to be looking at heap sort right now. So if we look here, like merge sort, the running time complexity of heap sort algorithm is n log n. All right. But like insertion sort, heap sort will sort in place. All right. So if you remember just now, merge sort, you need to create an auxiliary array to keep the element when you do the sort. But for heap sort, it will sort in place. All right. So therefore, heap sort is combining the better attributes between the insertion sort and the merge sort. And then inside the heap sort as well, it's introducing a new, not a new lah, but a different type of data structure, which is called a heap. Okay, so a heap is will look like a tree. Okay, so in a sense, heap sort will be using a heap to do the sorting. All right. Okay, so what is a heap? Okay, a heap is a binary heap, or it can be a tertiary heap. So so if like let's say a binary heap data structure, so basically it will have two branches. So it can also have three branches and so on and so forth. But for now we are just going to look at the binary heap data structure. Whereby it is a data structure in an array of objects where we can represent it in a complete, nearly complete binary tree. Okay, so the heap will look like a tree, and you can represent this tree in a form of an array. Okay, in a heap, each of the node, okay, will correspond to an element of the array. And then the property of a heap is that you have to make sure that all the tree is filled on all levels except possibly the lowest. Okay, and even the lowest, it has to be filled from the left up to a point. Okay, meaning in a sense, let me try to put one page here. So meaning in a sense, if like let's say I have a heap that look like this, okay, so each node will have two branches, and the last level, a heap can have something like this. Okay, it is not complete, so for these two nodes have no branches, have no children, but the branch is filled from left to right. Okay, so meaning in a sense, if you add one more element, it will go to this right, next element will go to this right, this element will go to this right, this element will go to this right. Okay, so basically that is the property of a heap. You have to make sure that it looks like this. Okay, so if like let's say you have a tree like this is not a heap. Anybody know why? Because you need to fill this one first before you can have a node here. Okay, so that is the property of a heap. So property of a heap, again, as I mentioned, it can be a complete binary tree, meaning in a sense all nodes will have a equal number of children, or you can have a nearly complete binary tree which has some of the nodes are filled from left to right. Okay, so that is the property of a heap. Okay, so bear in mind that would be how the heap tree will look like. Okay, and then you will have to know these two things, which is One is the A dot length, which is normally it is the number of element in the array, as well as the heap size. Okay, because later on you're going to see that inside the array, some of the element may not be part of the heap size. So therefore you need to keep track of these two attributes, okay, when you are dealing with heap. Okay, any question about this one? Yeah. Do you understand the complete and nearly complete binary tree for heap? Okay. All right. So for a heap, normally you can have a max heap or a min heap. Okay. So for the purpose of explanation in terms of the heap, I'm going to be using max heap. Okay. So for min heap, it's the other way around. So the properties are just the opposite. So I'm just going to explain to you what the max heap. Okay. So for the max heap, of course, it looks like a binary tree. Okay, so this is the binary tree. And as I mentioned, this is a nearly complete binary tree because as you can see, the last level, you only have these three elements is being filled from left to right. Okay, and then you can represent this in the form of an array. Okay, how do you fill it up? You see all this number on the tree on this node. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This can be represented in array 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, those are the index. So you can fill 16, 14, 10, 8, 7, 9, 3, 2, 4, 1. So in a sense, you fill it from left, you read the tree from left to right, and you fill it up inside the array accordingly. Okay, so this is how you can represent a binary tree in a form of an array. Okay, and then for max heap, this is something that you need to remember. Okay, so for the max heap, you have to make sure that parents are always, this is for the array. Okay, and for this one, we say that for this tree, it has the height of 3, meaning this is level 0, this is level 1, this is level 2, this is level 3. Okay, so that is the height of 3. And the node at index 4, so we look at index 4, has the value of 8. So if you look at our tree, index 4, we have the value 8. Okay, so that is how you will read a heap. Okay, and how do you compute the indices? So in a sense, if you have a binary tree represented in an array, you can just use this function. Okay, if in order for you to find what is the parent, you just use I over 2. What is the left child of that array? You try to calculate 2i, and the right 2i plus 1. So let's say, for example, we want to calculate for I over 2. Okay, so we want to find the parent of, let's say we want to find what is the parent of index 6. Okay, so let's say, for example, we want to find out what is the parent for this element. Okay, parent is in index 6, so therefore we just 6 divided by 2, which is 3, and we know that the parents of this element would be in index 3, which is 10. Okay, so if you look inside the tree, this is the I, and the parent is in index 3. Okay. Excuse me. So excuse me. So that is how you actually compute find out what is the parent, left child, and right child of a binary tree in an array. Okay, so you just use this function. Okay, all right. So for the heap, property, so as I mentioned just now, there are two kinds of binary heap. One is the max heap, which I'm going to be using as an example today, and the min heap. So for the max heap property, the property is that the parent will always be bigger than the child. Okay, so left child or right child, whatever it is, the parent has to always be bigger than their children. Okay, the min heap property is the other way around. So the parent will always be smaller than their children element. Okay, in the child branch. All right, so that is the heap property. So for the basic operation of the heap, you have max heapify. All right, so you have max heapify. You have built max heap. You can do sorting, okay, using the heap sort using the heap, okay. And in order for us to do the heap sort, we have to make sure that we do the max heapify and build max heap first. And we can also do max heap insert, extract max, increase key, and find what is the heap maximum or heap minimum for min heap. And normally this is for implementing the priority queue. Okay, so this is one of the main advantage of using heap is the implementation of priority queue. Meaning in a sense you can find the maximum or the minimum in constant time. All right. So let's look at each of the operation here. Okay, so for the max heapify, it is used to maintain the heap property. So if it is a max heap, it is to maintain the max heap property, which is the parent has to be bigger than their children. Okay, so this max heapify is called to do that. Okay. So here we see that maybe we're just going to straight away visualize how to do the max heapify. Okay, so like let's say we have this. Okay, so let's say we have excuse me. Okay, so let's say we have this heap or this binary tree. Okay, so inside our A, okay, inside here, we can see that and we know this is supposed to be our max heap, right? So therefore our max heap, we want to make sure that the parent has to be bigger than the children. So here we can see that which element, which node that actually violates the max heap property, class. So we have this node, right? Node number 4 violates the property. Do you see why it's violating the property?
It's greater than its children.
Okay, so basically this is the parent of these two elements, and it is smaller than the children. Therefore, in order for us to change it back into the max heap property, we have to call the max heapify. Okay, so how do we do that? The max heapify will look at this, and then it will try to find which of the children has the biggest number. So like let's say between 14 and 7, the biggest number is 14, and therefore we are going to swap 14 and 4. Okay, so now this becomes 14 and now this becomes 4. All right, so what happened now is the max heap, have we achieved a max heap property here, class? We can see that this one is still violating this one, right? This node is bigger than the parent node, right? So therefore, we're going to call the max heapify again on this node, and we're going to swap it out. So this one become 8, this one will become 2. So how about now? Sorry, this become 4. It's become 4. So how about now? Is this max heap? This is already max heap.
Yes.
Right? So each of all the element is following the max heap property. Okay, so that is how max heapify do the operation, okay, in order to maintain the max heap property of a heap. All right. Okay, so the running time complexity for max CP5 in this case, if you see, okay, how we do the max CP5 operation is that uh, uh, is that we will run it the height of the tree, and therefore okay, 1 second. Okay, so the running time for max CP5 would be the height of the tree. So what is the height of the tree? If you remember when we do our recursion tree recursion tree last time, it would be log n, right? So so we can always say that the running time complexity for max CP5 is defined as such, okay, the recurrence relation. And then using the master theorem will be order of log n, or we can always say that it is order of h, which is the height of the tree. Okay, so it will be order of log n. All right. So the next operation would be to build max heap. Okay, building a heap, whereby if like let's say we have an array and we want to build a max heap. Okay, we can use the max CP5 function to develop the max heap from bottom up, okay, whereby we start the max CP5 from the last parent up to the root, okay. So how do we do it? So if you notice here, the heap size is equals to the heap length, to the array length, okay, and then we're going to call max CP5 from a dot length over 2 down to 1. Okay, so why are we calling why are we calling a dot length divided by 2 down to 1 is because we know that the leaves sorry. So if like let's say we have our heap again, okay, let me just draw a simple heap very quickly. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So let's just put 8 so that will be easier. Okay, so let's say the a dot length down to 1. So which element is the last parent? What I mean is that the last node that have at least one children. So we know in that case, so we know that the last node that have at least one parent is this one, right? So we need to do max CP5 starting from this one up to the root. So we're going to do max CP5 on this node, this node, this node, and this node. Okay, that is how we're going to traverse back up the heap. Okay, so how do we find what is the last parent in the tree? Is we can, like I say, 1, 2, 3, 4, 5, 6, 7, 8. So we'll take floor 8 over 2, which is 4. So we know that the last parent would be node 4. 1, 2, 3. It will be 1, 2, 3, and 4. So therefore, we're going to do max CP5 from this node, okay, up to the root. So it is the same thing again. So like let's say we have this array, okay, we have this array and we represent it in a form of a binary tree, okay, and in this case we have 10 elements. So therefore 10 element, we will start max CP5 from node number 5, which is 1, 2, 3, 4, 5, which is the which is this node, right? So we're going to do max CP5. Remember how we do max CP5? we're going to look at the child. If there's a child that is bigger than the parent, we're going to swap it up. Okay, so in this case, this one is fine, right? So we go to the next one, which is note number 4. How about this one? Is this maxip? Do we need to call maxipify on this class?
Yes.
Right?
Yes.
So we're going to sort which one up?
14.
So this one would be 14. This one would be 2. Okay, so that one is done. Then we go to the note number 3. Is this maxipify? Is this maxip? No, right? So 10 is bigger, 9 is bigger than 3. So we're going to sort out the biggest number, which is 10. So this will become 3, this one becomes 10. Okay, and then we go to the next one. Next note, is this maxip? No, it violates maxip property. So between 14 and 16, we're going to sort up 16 up. So this one will become 1, this one will become 16. So finally, the root 4, and we have 16, 10. We're going to swap 16, sorry, we, for the 16, sorry. This one we haven't finished because we need to traverse down. So this one becomes 16, 1. Okay, so now here is 1. I always forgot to go traverse down. Okay, so now this is 1. So still, this one is still it's violating the maxip, right? So we're going to sort this one again. Remember maxipify, we are going to traverse down and make sure that we have the maxip property checked. Okay, so this one becomes, this one becomes 1. This one becomes 1. Okay, and then we go to the last note, which is 1. So 4 compare, so we have we send up 16. So this one becomes 4, this one becomes 16. So again 4, it's violating 14 and 7. So this one becomes 14, this one becomes 4. So this one is violating again, so we're going to transfer 8 up, and this one becomes 4. Okay, and now we have our max heap. Okay, so is it same? We got 16, 14. We have 16, 14, 10, 8, 7, 9, 3, 2, 4, 1. Okay, so we build max heap using maxipify. All right, so that is how you build max heap. So again, the running time complexity for build maxip is that you will call maxipify for all the order of n calls, or maybe like up until the parent. Okay, so therefore the running time complexity is order of n log n. Or if you want to do a more tighter analysis, which whereby you consider like calculating calling the maxipify only on the parent, the last parent of on all the parents in the heap, we can also do something like this. I'm not going to go through in details about this one. So in a sense, if we look specifically into that, we're going to get the running time complexity for build maxip is order of n. Okay, which is, so basically the running time complexity for build maxip is between n log n and n. Okay, all right. So how do we do the heap sort using the heap? Is that, so you know that when we build max heap, what can you observe from that tree? If we look at this tree, what can you say about this tree? What can you say about this tree?
The just element starts at index 1.
Okay, so basically this one would be the maximum or the largest value, right, in the array. So from that information, we can do our sorting. Okay, whereby we can always extract the max, and then keep extracting the max from the heap. So how do we do that? So heap sort, how do we do the heap sort is by extracting the maximum element onto the heap. Okay, So first, of course, if like, let's say you have an element, okay, first you need to build your max heap. You need to call your max heap so that you will have your max heap. And then what you do is that you know that at A1 it would be the maximum, right? So you always extract the maximum. And how do you extract it? Is by exchange it with the last element in the array. So or is it like if like let's say you have these three, you always swap this with the last element in the array. Okay, and then once you swap it, so basically the maximum would be here. So inside the array, so your maximum would be in the last element in the array. So therefore, you decrease the heap size. So basically the next heap, so this one is not, the last element is not in the heap anymore. And you are going to max heapify the rest of the element. And you keep doing that. So after you max heapify the element, the array again, you do the same thing. You extract it and you swap it with the last element in the array, and then you do it again. You max heapify again, and you try to get what is the maximum inside this the element that is left in the heap. Okay, you keep meaning in a sense you continuously reducing the heap size by one. Okay, so basically that is how the heap sort works. Okay, so looking at the thing here, so let's like just do it again. So we know that this one is the maximum, and we swap it with the last element. Okay, and then we do max heapify, and we're going to get this heap with this element already sorted at the last place. Okay, we do the same thing again. We're going to swap 14 with 1. We do max simplify, and then we're going to get these 3. And these 2 is already sorted. Same goes. We again, we swap 10 with 2. We do max simplify, and then we get these 3. And then we get these 3 elements sorted. Again, we swap 9 with 2. We max simplify, and now we get this heap with this element sorted. Okay, and you keep going until you reach the root, and therefore you will finally get a sorted array. Okay, any question about this one so far? Okay, so for the build max heap, it will take order n log n, because to build max heap, it will take order of n time, and each time it will call the max heapify, which is log n, and therefore the heap sort, the running time complexity is n log n as well. Okay, and as I mentioned, for the heap, it is good. It is actually that one of the advantage is that it can properly implement the priority queue. So as I mentioned, the nearest competition of a quicksort is heapsort, but most of the time a good implementation of quicksort usually beats heapsort in practice. But for heap, it is good for priority queue, because you can actually extract maximum in constant time. Okay, because once you have the max heap, all you have to do is just extract the root, and you will get the maximum value in the array. Okay, so for the max priority queue, the operation that you can have is you can have insert, maximum, extract max, increase key. Okay, so same goes for the minimum priority queue. So basically the heap property would be the min heap, and you will still have the same operation for the priority queue. Okay, so for the max priority queue, in order for you to find what is the maximum, all you have to do is just return A1. So the running time complexity for that is constant. Okay, order of 1 time. For the extract max, is also constant. So in a sense, you just extract the maximum, but then you still need to do max simplify, because once you extract the max, it's just like when you do the heap sort, you exchange it with the last element and you still have to max simplify the heap. So therefore, the running time complexity is log n. Okay, meaning in a sense, you just have to run the max heap. Okay. And then for the heap increase key, same thing. You choose which key to increase, and then after that, you sort of like traverse up to the tree. So let's say, for example, we have this heap, okay, and you want to increase this element to 15. Okay, so what you do is that you will, once you increase this key, you will look at the parent. If it is smaller, you stop it. Okay, so 15 is going to go up. So now this one will become 15. Again, you look at the parent. If it is small, you swap up. So this one becomes 14, this one becomes 15. And that's it. Okay, so in a sense, you look at the parent and see whether if it is smaller, you just swap it up. Okay, so that is how you increase a key. Again, the running time complexity of a key is the height of the tree, which is order of log n. All right. Same goes for insert. How do you insert? Is that if, like, let's say you have a heap, you create a new node and you assign it to the value negative infinity. Okay. And then you are going to increase the key. Okay, so you will use this function. So in a sense, this one, you will have you will create another node here of negative infinity, and you will increase the key here. So the new key would be here. Let's say, for example, I put 4 here, and you will do the same operation as heap increase key. Okay, for you to when you do the max heap insert. And in this case, the running time complexity for that is also order of log n, which is the height of the tree. Okay, so yeah, so that is how you use heap for priority queue. So I guess I'm going through that quite fast, but I think it's you should understand it no problem if you really understood how you use the heap. Okay. And here I also include additional common problem that is being solved using command and divide and conquer. Okay, binary search algorithm. I believe we have touched that during our tutorial. It is actually a divide and conquer algorithm as well. So in a sense, how does it it does it is that during the divide phase, it will check the middle element, and then recursively search the one subarray. So if, like, let's say the search key is lesser than whatever that is the middle element, you either go to the lower or the upper subarray. So that is a divide and conquer algorithm. Okay, so I'm not going to go through this one with you right now. You can also look at powering a number. Okay, so powering a number can also be solved using divide and conquer as well. So again, you may go through it and see Fibonacci number. Okay, so you can also use divide and conquer for calculating Fibonacci number. Okay, using recursive squaring. Matrix multiplication. All right. So these are some of other example of the divide and conquer approach to solve some problem. Okay, so you may have a go through it, and then in case you want to know further. All right. So do you have any question in regards to today's lecture, class? Class? Are you all good?
For the most part, towards the end. Yeah, for the most part, okay.
Okay, so towards the end, which is the priority queue, is it, or the heap?
Priority.
So for the priority queue, the concept is just that if like let's say you have an element and you want to find like let's say for example you want to find what is the maximum number, or maybe you want to increase some keys and you want to keep the properties in check, like always have them. Normally when you talk about priority queue, you want to know what is the highest priority element in the array, right? So in order for you to get what is the maximum element in the array, a heap is one of the best implementation that you can use, because first the building of the heap is log n, okay, n log n at most. And then the extraction of the maximum element is either constant. It's all most of that it is actually constant, because the root will always keep the highest value. Okay, so that is the concept of the priority queue. So the rest of the one that I fly through is actually just how you can actually maintain the property of the max heap or the min heap in the priority queue. Okay, so maybe have a look at it again. If you have any question, we can tackle it during tutorial. Okay, so I think we have a lab for this week. I haven't looked at the question. So if you have any question, we will discuss further during tutorial. Is that all right?
Okay.
So reminder again for those who are going to have a Viva tomorrow, please make sure that everybody knows the solution that you have provided. Okay, so because the question will be randomly asked among the members. Okay, all right. So thank you. In that case, I will see you in tutorial and the lecture next week. Okay, thank you everyone. Assalamualaikum.
Good.
Bye.
Yeah, the
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Bye.
Doctor.
Thank you, Doctor.
Thank you, Doctor.